So we should be starting in just a moment. As usual, if anybody has any questions, then send them my way. There might be two different pieces of homework this week just because of age groups, but I'll give you a few minutes to let me know if there's anything in particular across the chemistry that you did and possibly even the week before biology, depending on which day of the week everybody did it. I need to move this out of the way. I'm not doing that. Who's that? Can you do the question one different? Yeah, trying to energetics. Yes, I will start with that. Um, as I say, anybody has any questions in the meantime, please do tell me. If you have any problems in seeing anything, then tell me because I think we're okay. Um, and again, when you ask for the questions just on the booklet, just confirm. I think I know when you ask, but just confirm which subject, whether you're asking about biology or chemistry. Only because a few people will have done the chemistry that everybody else did at the weekend yet. It's just a bit confusing. Um, yep, year 10 chem, fine. So far, year 10 chemistry, 1 to 4, and well, 1 to 4, essentially, which includes 3C, so we can deal with that. Right, I'm going to start with those questions that have just been asked. So let's go here, because that's where it is. Not that one. This one, right. Just to be clear, this booklet on that you guys have had on energetics is, I would say, pretty challenging. I'm just going to keep the answers because I do have the answers available. Right, let's have a look. How do you know that the reaction is exothermic? Right. When you look at these graphs, just to put it very simply, an exothermic reaction graph should look like that, and an endothermic graph should look like that. In other words, in an exothermic, as you go left to right, you go down, that's exo, and as you go left to right, you go up if it is endo, because, and that's what the question is, it's because this final position represents the energy of the products from this chemical reaction, whereas this starting point represents the energy of the reactants. So how much energy you start with versus how much you finish with. Given that the reaction is exothermic, to explain why, you just want to say that the energy of the products, which is here, is less than the energy of the reactants. And that is that. I'll just see what other questions people have got. Chemistry paper one topics, hydrogen fuel cells, required practicals. Yeah, I'll do the required practical certainly, and I'll show you hydrogen fuel cells, and I'll do the year 9 things from that as well. Um, okay, fine. Next question on here. Explain in terms of energy how the platinum catalyst increased the rate of reaction. Now, what you're supposed to know about a catalyst is that it lowers the activation energy. That's what a catalyst does. You must say activation energy. So the activation energy is this bit here on the graph. Now, if you add a catalyst, essentially the graph does, it sort of starts and finishes at the same point. It just doesn't go as high. So you have a lower activation energy when you add a catalyst. Right, part B here. Right, I really shouldn't have to explain this, but I shall. Because there should have been enough examples that you did in class that should have covered this. Right, let me do this one, and then we'll see. So these are the questions that you will almost certainly get regularly in certainly paper one chemistry if you are doing AQA. But regardless, they'll be somewhere. So how shall I do this? I think I probably need a calculator, so I'll just have one ready. Yeah, there you go. Right. I like to put brackets around things in these kind of questions, because otherwise I think it's easy to miss the fact that there's a number outside each of these things. So what do we have here? We've got a CH bond, another CH bond, another CH bond, and another CH bond. So four CH bonds, and each CH bond is worth 435. So I'm going to do four lots of 435 here, but I'm also remembering that everything's being times by two. So I'm going to include that two times. I'll explain this afterwards. We'll just get to the right answer. Plus O double bond O, which is 498. So when you do these questions, what you want to do is work out your number for the left-hand side of the arrow and then your number for the right-hand side of the arrow. On the left-hand side, we've now got 2 times 4 times 435 plus 498, which is 3978. That's what we get on the left-hand side. Let's do the right-hand side now, which is a bit of a pain, but we've got CH, another CH, another CH. That's three CH bonds, which is 3 times 435. We've got a CO bond, which they tell you is worth 805. So add on 805. And we've got an OH bond, which is 464. And don't forget, all of this is being times by 2. So you need to do a 2 times at the end of all of this. So 3 times 435 plus 805 plus 464 is 2,574. If you times that by 2, it gives you 5148. I assume I'm doing this correctly. Easy to make a mistake on these. Once you have got a number for the left-hand side, a number for the right-hand side, you do the left-hand side number, take away the right-hand side number. So 3978, take away 5148. And that should give you, if I haven't made a mistake, the overall energy change of this reaction, which is minus 1170. Right, let me explain what we've just done, though. I think it's important because usually a subsequent question asks you to explain a little bit about what you've just done. So the number that we worked out on the left-hand side of this is, so I've just done this lesson now, but in any chemical reaction, on the left-hand side of it, so the left-hand side of the arrow, this side of it, we are breaking the bonds that there are there. That's what we're supposed to be doing. We need to break everything into pieces and then put them all together in a different order, a bit like Lego, where you're breaking everything and then making new stuff with the same pieces. This energy that we have just worked out is the total energy that we have to take in, or the reaction has to take in, to break the existing bonds. So on the left-hand side, we have the existing bonds. We're trying to break them. On the right-hand side, we have the new bonds. And when you make new bonds, you release energy. So on the left-hand side, energy is being taken in. On the right-hand side, energy is being released. So this number is the energy released to form the new bonds. Okay, and to explain why this reaction was exothermic, exothermic is when energy is released overall. You need to explain that more energy was released to make the new bonds than was taken in to break the existing bonds. So we need to explain, and this is the only way to answer this. More energy is released, forming the new bonds on the right-hand side than is needed to break the existing bonds on the left-hand side. There is really only one way to get any marks on this question. You have to say it in that way. You can't just say because energy is released, because that's what you know exothermic means. For these kind of questions, you have to explain it in terms of making and breaking bonds. Okay. Can you not say the energy in the product? You can't say that. So the question is, can you not say that the energy in the product is less than the energy in the reactants? I think that's what you meant. Like we saw when we had one of those graphs, right? So this is an exothermic graph, right? And the energy in the product is more less than the energy that we started with in the reactants. You cannot do that. I'll tell you why you can't do that. Specifically because the question says in terms of the bond energies. Because what you're answering, if you say because the products have got less energy than the reactants, that's not in terms of the bond energies. That's just in terms of the energy in the actual final chemical, which I appreciate doesn't make much sense. But when you see this kind of question after one of these calculation questions, these bond calculation questions, you have to say it in this way. Okay. It is just an annoying requirement. Right. Questions 1 to 4. There's a bit more to go, then I'll move on to the other stuff that people have asked me. I'm once again, I'm not answering every question because again, you should know how to answer this question if you know what relative formula mass is. It is just, I mean, it's fairly obvious what the answer is, right? It's got surely these numbers add up to this number at the bottom. I'm also not going to answer that question or this question. What does exothermic mean? Exothermic is when a reaction releases energy to the surroundings. So heat energy is transferred to the surroundings. That's what it means. Okay. Um, Carbon. Which two statements explain why carbon dioxide? Now, again, there's a lot of topics that overlap here, but you are supposed to know that carbon dioxide is a covalently bonded molecule. So it's like carbon there, and then there's like two oxygens joined to it. That's why it's called CO2. Now, when we have these things called simple covalent molecules, they always have very certain properties um, such as they have low melting and boiling points. And because they're simple and small, they are small. And so that's kind of the answer to this question. It is not made of ions because that means it's an ionic bond. I just explained that it's a covalent bond where there's the sharing of electrons. It's not a giant structure. That's the entire structure. So it's not a giant structure. It's actually very, very small. So that was that, right? Question 3. This is quite difficult. There's a part of this question that is really hard, so I'll explain the answer. To be fair, it is unlikely that you cover this in the lesson, which is why it sometimes happens. A student investigated the temperature change in displacement reactions between metals and copper sulfate solution. Okay, so when they reacted copper sulfate solution with copper, there was no temperature increase, which is true because then displacement reaction is when a more reactive metal kicks out a less reactive metal. So if I've got copper oxide and I react it with something like iron, because iron is more reactive than copper, it kicks out the copper, leaving you with iron oxide and copper. But that only happens if this is more reactive than the original compound metal. So and usually when a reaction happens, there's an increase in temperature. The fact that there's no increase in temperature tells us that nothing happened when I tried to react copper with copper sulfate. And because you wouldn't expect anything to happen, because something would only happen if this metal is more reactive than the metal in the compound. And obviously it's the same, so it's not more reactive. Iron is more reactive than copper, so we get a temperature increase. Magnesium is more reactive, it kicks it out, we get a big temperature increase. Zinc is a bit more reactive, we get a bit more of a temperature increase. So I don't know what the next question is, but if the next question is to, not the next question, is to explain which is the most and least reactive out of all of these, you just order it in terms of the temperature increase. So the least reactive would be copper because it didn't do anything. Then we would have iron, then we would have zinc, and then we would have magnesium if it was in order of reactivity, which is probably not the question. Plot the data from the table above as a bar chart. I don't think I should need to do this. You just need to get your scale correct. So you might do something like, I don't know, 10, 20, 30, and 40. And then you just draw a bar. Is this a bar chart? Yeah, a bar chart. So copper would just be like 0. Iron would be 13, so you'd do a bar up to 13, and then you'd continue with the other ones. That should be easy enough. Right. The student concluded that the reaction between the metals and the copper sulfate solution are endothermic. Give one reason why this conclusion is not correct. Endothermic means that heat is taken in from the surroundings, and therefore the surroundings get colder. In this case, we saw a temperature increase. So therefore, this is obviously not endothermic, it's exothermic. Okay, and then this is the question that specifically has been asked. The temperature change depends on the reactivity of the metal. The student's results are used to place copper, iron, magnesium, and zinc in order of their reactivity. Describe a method to find the position of an unknown metal in this reactivity series. So, um, it depends on the method here. It's quite a complicated. So what we could do, is this the same question as we used to place? I'm just checking what we actually did here. We reacted it with copper sulfate solution. Oh, fine. That's not that difficult. What you would do is you like look. We know that it goes copper, whatever I said earlier, copper, iron, zinc, magnesium. Okay, and in terms of the temperature change, it was zero. What was it? 13, 17, and 43. So what you would do, so what we're saying, it's not very well worded, the question. It's that if there was a, let me just check if I'm missing anything. Yeah, I'll do the, again, if you're asking questions about the booklets, it's fine. I know where you are. You're on the weekend. So it's on Saturday and Sunday, it's chemistry. It's fine. Um, so the, it's not worded very well, but what we're saying is that if we had something else that we didn't know, an unknown metal, if I had like, I don't know, something in my hand that was an unknown metal, and I said, where does it fit in this reactivity series? Well, what you would do is you would do exactly the same thing again. What did we do with all of these? We added them to copper sulfate solution. That's what we did in this original reaction. So that's why you want to make sure you read these questions carefully. We add the copper sulfate solution and we would measure the temperature change. Surely that's what we would do, just like we did with these four. Okay. Um, and then we would put the metals in order of their temperature change. So if I had a temperature change of 15, then we know it fits in there. You see what I mean? Now, there's a bit more to this question, which it says your method should give valid results. That means that you need to explain what there's a little bit of a practical question, what your control variables would be. So what would you have kept the same when you did this experiment? Well, however much copper sulfate solution you used every time should stay the same. The mass of the metal that you're using. So if you're using, 5 grams of copper, then it should be 5 grams of iron, 5 grams of everything else. Um, Otherwise, you're going to get invalid results or not a fair test. So that's how you go about answering this question. Yeah, that's it. Okay, and then draw a reaction profile diagram. Well, we know it's an exothermic reaction, don't we? So because it gave off heat, so you just need to do an exothermic graph where this goes below that. Fully labeled it once. Jeez. Right. Okay. So fully labeled means that you need to say that this is the energy of the reactants. Make sure you write that out. This is the energy of the products. From here to here is the overall energy change. And I don't know if you need the fourth one, but I'll do it anyway. From here to here is what we call the activation energy. Okay. Hopefully that is sufficient. Can you use the polystyrene cup practical from temperature changes for that question? Yes, is the answer to that question. There are a few different ways of doing that question. Um, in other words, you're measuring the temperature. But the only reason I wouldn't do that is because they've already done they've basically done the same experiment already. Because in the polystyrene cup thing, I mean, all you do is you mix some chemicals together and you measure the temperature change. They have essentially done that's it, that's essentially the practical that has been done here. They reacted it between metal and copper sulfate solution. The point of the polystyrene cup is that you keep the heat in because you're measuring temperature change. Now, I know we didn't say this, but probably they would have used a polystyrene cup when they did this experiment. I know they don't say it, but it's the same experiment. So it's not like that's a different practical altogether. It is the same practical. Um, yeah, essentially. So they just don't mention it. Because if you're measuring temperature, you're basically doing that polystyrene cup practical. Um, and then I think you said 1 to 4, so I'll just finish this. I'm not going to answer that question because I've already done it. I'm also not going to answer what the products of this reaction are because that's relatively straightforward. Um, in this reaction, one substance is reduced. Right, that's a tricky one. It's not that tricky actually. In basic chemistry, the word reduction means the loss of oxygen, and oxidation is the gain of oxygen, which I appreciate if you guys have heard of something called oil rig, that will seem confusing, but oil rig is specifically about electrons, not about oxygen. Um, and in this question, it says, name a substance which is reduced. Reduced means that we've taken oxygen away from something. Well, we had chromium oxide in this experiment, and it's ended up being chromium. So have we not removed the oxygen from that compound? Therefore, the thing reduced must be the chromium. What happens to the substance when it is reduced? I'll check what the mark scheme says for this. See, because it just depends on how complicated you want to make the answer. You surely can say oxygen is removed. Yeah, you can say oxygen is removed for that one. But if you want a more technical answer, you can say electrons are gained. Um, and then is that it? Right, that's it. Right, fine. That was all that. I don't think there's anything else that anybody specifically asked. Oh, 6 and 7. Okay. I can have a look at it. Right. These are not easy, I'll say. I'll see what I can go through. So 6 and 7 on this one. Methane and oxygen react together to produce carbon dioxide and water. 818 kilojoules of energy is given out, right? Which tells me it's an exothermic reaction to the surroundings. For each formula mole mass, each mole of methane that reacts. Okay. The methane gas will not burn in oxygen until a flame is applied, but once lit, it continues to burn. Explain why energy must be supplied at the start, but it continues itself once started. Well, it's quite difficult, this one. So you want to say that the energy that's supplied at the beginning is essentially the activation energy. The whole point of that activation energy is that it is the energy used that's needed to break the existing bonds first. You want to say first here to explain that in order before a reaction can take place, you need to break all the bonds, and only then can they start sort of colliding with each other. Um, to first break bonds. Let me just see if maybe asking more questions. Oxygen being gained, we said oxidation. Oxidation for gaining, reduction for losing oxygen. Um, First break the bonds, right? So we first break the bonds. That is why we need energy at the start to start it off. It's to break those bonds. Um, you could also mention something like you need more energy for the collision thing, if you want to think of it in rates of reaction terms. But I think that's fine. However, and then you want to say that why it continues by itself afterwards is because the overall reaction is exothermic. So overall, it is exothermic. So once that thing has begun, it now releases energy, which means it can continue by itself. It just needed that energy at the beginning to get it going. After that, it releases energy, which means that we don't now need to keep supplying it with energy. So if you say that the overall reaction is exothermic, you're good. Um, yeah, fine. Oh, I might add more actually. Which breaks, this is 4 mark questions, it's quite a lot actually. Which breaks more bonds so the reaction continues? Okay. Fine. Okay. And then you did say 6 and 7, so I'm going to see if I can go through all of this. Energy level diagram should be easy enough. It's an exothermic reaction, so it should be good. Question 7. This is an endothermic reaction, slightly unusually. How do I know it's endothermic? Because we start off lower than where we finish. We have increased in energy from where we started. And the question will ask you to explain the significance of X, Y, and Z. You should make specific as the bonds broken and formed into the net. I don't know why there's two T's on net. Net energy transfer to and around. Okay, so this is the last one I'll do from this one, I think. How do you reckon if the energy stops being supplied for question 6? Because energy is being released. Because it's an exothermic reaction, energy continue once it begins, it releases energy. It's like starting a fire, right? You know that energy is being released when you're burning a fire. So energy now continues to be released, and that energy can do what the previous energy was doing, like breaking the bonds. That's the point. So you just need it to get started, and then after that, you've got enough energy being released that will continue to supply it as an ongoing basis. It's just starting it off that you need it. For this question, explain the thing with X, Y, and Z. Okay, well, X is the activation energy, isn't it? Activation energy is from the lowest point to the top bit. So I would say X is the activation energy. Um, but we need to explain that a little bit better than this because it is, just like in the previous question, it is the activation energy is the energy you need to take in at the beginning to break the existing bonds. Okay, that's what that is. So that's how you need to, because the question specifically says referring to bonds broken and formed, you obviously have to do what it says. So that's why you need to say this. Otherwise, normally, if it was activation energy, I would just say it lowers it's the energy needed to start the reaction off. But you've got to be very specific about breaking the bonds here. X, Y, and Z. What's Y? Y. See, Y on its own isn't. Oh, right. Okay. Um, Well, let's come to, oh, actually, no, I can do that. Y now is the amount of energy this is quite a difficult explanation, to be honest. Hmm. So this is the energy that we took in, all of that, and then this is the energy we've released. You see what I mean? It went up and then it went down. So Y is the energy that we've released. And what does that end releasing energy? When does that happen? When we're forming new bonds. So it's the energy released when forming new bonds. So again, because it specifies breaking and making, we need to say these things in this question. Um, I'll get to the previous years, the year 9 questions. I will get to that in just a moment after this question. And lastly, these questions, what's Z? Z is the essentially the overall energy change, isn't it? That's what Z is. But you can also calculate what it is because it must be 1856 minus 1370. So you can actually work out what it is in this question. Right, I think that's all I'm going to do for that. Yeah, I appreciate that these. Then it's not the easiest homework, which is why once again your focus is notes. Um, right, let me just move on to anybody who's asked questions from the other one, and then I'll do one of the topics that has been asked was um, about the required practicals a little bit, so I can do that, and I'll show you hydrogen fuel cells briefly as well. Um, so that's not the one. We're doing this one. Right, I'm just going to go back to the top. Oh, there's Tallier's principle as well. Okay, I should be able to do that. Um, Question one from part C2 on the Year 9 booklet. Question four, 1C. I'll just do all of question one and question four then. Shouldn't take too long. Right, complete the word equation for this reaction for hydrogen and water. You want to, the best answer to this question is water, but if you put something like hydrogen oxide, it is also allowed according to the mark scheme. This shows one of these, which we've seen loads of in a minute ago. Which arrow represents the activation energy? So the activation energy is from where we started. So again, looking at it left to right on the graph, where you started is here to the highest point that it reached before it began to decrease. That would be A. So that is answer to that question. What type of reaction is shown by the energy level diagram? So if you finish lower than where you started, then we have lost energy overall, and it is an exothermic reaction. So what you want to say, to be precise about this, is that the energy of the product is less than the energy of the reactants. That's the energy of the product. It is lower than the energy of the reactants. Okay. All right, on B still. For the reaction, the value of A is 1370, C is 3230. So calculate the value of B. I usually do one take away the other, don't you? Yeah, because if that's B, and that's A and that's C, then the difference between C and A is what B is. So you would just do that, take away that, and you should be fine. Right, I'm not sure how you would have known this. Some of these questions just throw in topics that you are not expected to know too much about yet, but this is still relevant for everybody else more. So alcohols are used as fuels. A group of students investigate the amount of energy released when different alcohols are burned. This shows the apparatus in figures two. So there is some alcohol in here, and alcohol can be used as a fuel. It can burn. So they're using it to seemingly heat up some water. Looks like it. And then they're going to measure the temperature, I guess. Figure three shows the start temperature and the final temperature of the water. Write the start temperature and the final temperature, and then work out the increase in the temperature. Okay, just be very careful with your scales here. If that's 22 and that's 23, then this must be 22.5. So it's going up in 0.1s, 20.2.1, 2, 3, 4. That's 22.5 by my reckoning. Okay, and then presumably this is the same. It's going up in 0.1, so that's 38.5, 6, 7, 38.7. And then the increase in temperature is the difference between those two numbers. Please make sure you use a calculator for these kind of, for anything in science. Please make sure you use a calculator for every single small calculation, because it is not worth getting it wrong. Right, then. The students worked out the heat energy released by burning 1 gram of each alcohol. The student used the equation heat energy released is M times 4.2 times increase in temperature. What is the value of M? Um, is it, did it tell you in the question? That's a difficult question, but it's the 50. It's the mass of the water. Um, yeah, it is that. I can't really say much more. Um, yeah, that's what it is. You're supposed to go back and read the question from earlier. And then C part three. Okay. What they did was they tried lots of different alcohols, and each alcohol, in terms of its chemical formula, gets slightly bigger each time. That's 1 carbon, that's 2 carbons, 3, 4, 5. And then what they're doing is they're showing the heat energy released each time. So they did the calculation using that formula that we just did. Now, they're asking you which of these results is anomalous. Anomalous basically means wrong or doesn't fit the pattern or something has gone wrong to suggest that has happened. Um, the which was wrong? Well, it looks like it goes up and then up Hmm. I mean, it's got to be that one, right? Because it shouldn't have gone up that much. So it's gone 11.4, then 13.5, and then this one was 16.8. This one was 17.2. This one just seems out of place. Um, because it just seems to be way higher than everything else, which just seems wrong. So that's the 20.1 is the anomalous or wrong result, I suppose, or one that doesn't fit the pattern. Look at table two. What is the relationship between the number of carbon atoms and the heat energy released? Well, as the numbers of carbon atoms increase, as you can see there, what happens to the energy released? Excluding, let's say, this one, because a mistake, obviously. It still is showing an increase, right? As the number of carbon atoms increase, the heat energy released increases. And that's what you want to say. So as the number of carbon atoms increases, don't do arrows when you're writing your answers. The heat energy given out also increases. Okay, that was that. Let's see. All right, there's so many questions here. The value in a data book for the amount of energy released when 1 gram is burned is 36.2. So what they're saying is this butanol stuff, they got a value of 16.8, but when they read it in a book, it said that it should be 36.2. Um, and there's a few different answers for that one. But I'll just tell you what the answers can be. In this experiment, they did not use a lid for a start. Um, they could have used like some sort of insulation, like the polystyrene cup or something like that. Because the issue is with you when you do this, a lot of the heat just gets lost, and so your thermometer is not tracking as all of it. So a lot of it is going into the air. So you want to the fact that there was no lid would be a sensible answer to that question. So they got a much lower number. So you can say there was no lid, or they may have just measured it wrongly. Now, this isn't usually a mark, but the mark scheme does say it. So you can just say inaccurate measurement. So they just didn't measure it correctly. Maybe they read the thermometer wrong or something like that. That could have been a reason. Or you could have said that it just might have been a wrong result. So they should have repeated it and calculated an average. Because that's what you normally do in science experiments. You do lots of times and you get to an average. Um, That was that. And then, I mean, I'll just tell you the answers because there's no way you're meant to know this, but the answer is that one for the OH. And then that, I think, and then there was another one, wasn't there, from this booklet. And then I'll just answer. There's one question from the last week's biology, which I'm just going to quickly do as well. Um, just because the order of lessons was all wrong. Um, yeah, no, in booklet question four. Question four. On the energy level diagram, what is represented by the letter A? So the difference between the line that we started at and the line that we finished at is called the overall energy change. And the distance from where we started to the highest point is called activation energy. Okay, once you do this enough repeatedly, it gets quite predictable. Um, And what type of reaction is this? Well, if the overall energy change has gone down, it means that we have released energy. It means that it is an exothermic reaction. I've missed an answer, haven't I? I missed out what C is. C is the energy level of the products. So the products are what we finish with, reactants are what we start with. Okay, that's it. That's the only one you asked me. Right, so very quickly, question two, year nine, bio. I've got it prepared. Um, so I appreciate this is last week for most of you. Um, Question two. All right. The cells that control the size of the stomata, I'm sure a lot of you know, are called the guard cells. The scientists grew tomato plants in air containing different concentrations of carbon dioxide. Let me just keep this answer available to me so I can tell you what these are. Um, They recorded the number of stomata found on the lower surface of the leaves of plants grown at each carbon dioxide concentration. It's quite difficult to get your head around what's happening here. But what we're saying is that when we grew a plant with a small amount of carbon dioxide in the air, they tended to have a lot of stomata, whereas when there was loads of carbon dioxide in the air, they tended to have very few stomata. And the reason for that is that obviously plants need carbon dioxide. And if there's very little of it in the air, so low numbers, then they need to maximize how much of it they can get in because there's so little available. And so they have those plants tend to have more stomata. Stomata are the things that let in CO2 because they're trying to increase the likelihood of them getting it, essentially. Um, so the relationship between the mean number of stomata and carbon dioxide concentration, the first mark is to say that as the CO2 concentration increases, the stomata number decreases. Okay, so as that decreases, this increases. Hopefully that makes sense. But there's always another mark for these things, okay? And I was saying this to the students I just taught. But whenever you see a graph that is not a straight line, so if it was a straight line, it would be like that, right? And it would probably be a 1 mark question that says, as that increases, that decreases. Done. But you need, if it's curved, you need to explain why it's curved. So you need to explain that at the lower amounts of carbon dioxide, the drop or the decrease is much greater than it is here. Okay, so there's a bigger decrease at low carbon dioxide concentrations, whereas as you get higher ones, it's not as drastic the change. Okay, so bigger decrease at low CO2 concentrations. Okay. And then a reason for the relationship, I sort of explained this already, but the reason for it could be that when there's more carbon dioxide, it doesn't need as many stomata. Or you can say the opposite. When there's less carbon dioxide, it needs more stomata to be able to get that CO2 in. Okay. Um, a disadvantage of having a large number of stomata, as well as stomata allowing carbon dioxide in, they also, whenever stomata open, the plants lose water. So a disadvantage of having a lots of stomata is that the plant may lose too much water. Uh, Suggest one environmental condition where a large number of stomata would be a disadvantage. Well, I guess if it's hot or dry and you're losing loads of water because of all the stomata, then that would be a disadvantage. I'm not going to do the, no, that's it. That's the whole question, isn't it? Um, um, I'm not sure which bit. Oh, that bit, right. Okay, let me do this bit as well. So, I presume we're talking about this bit. So you want to say for this one that as the concentration of CO2 increases, the number of stomata decreases. I presume that's the bit that wasn't very clear. And you want to then say that there was a bigger decrease at lower CO2 concentrations. Right, that hopefully is enough for that bit. Right. What else is here? Right, let me see. Okay. Now, the next bit I'm going to do, I mean, if you're in year nine, you're more than welcome to stick around, obviously, but it will be more applicable, I think, for the older students in terms of specifically the topics that have been requested, which seems to be the reversible reactions, Le Chatelier's principle, and the required practicals, which are very much things that you tend not to do until a bit later on, and hydrogen fuel cells. Um, okay, I'll start in order that it was asked. So Le Chatelier's principle. I'm just going to do one example, the example that we do in every single lesson that we do on this stuff, which is that this is the symbol for, oh, not that one, a reversible reaction. A reversible reaction is one that can go both ways. So what that means is whatever's on this side can turn into what's on this side, and whatever's on this side can turn into what's on that side. Now, which is annoying if you think about it, because if you're trying to make one thing and it keeps turning back into the thing that you started with, it's a pain. But that's what we have here. So I'm going to just use one example of a reaction, which is hydrogen plus nitrogen gives ammonia. Okay. Um, and there is a balanced equation for this, which is something like this. Right. When this reaction happens, okay, let me just try to do a very, very quick explanation for people. We have, let's say, hydrogen and nitrogen on this side. What happens is these start hitting each other, okay? And at the beginning, there is a really fast reaction. For those of you who did rates of reaction, when the concentration is very high of everything, there's a fast reaction. So there is a very fast reaction to start with because there's loads of these things. But gradually what happens is, as these get used up, the rate of reaction slows down because now there'll be fewer collisions, right, between all of these. And so the rate of reaction from left to right starts off really fast and gradually sort of decreases like this kind of graph. Now let's move to the other side. As this was happening, we were turning these into ammonia, but then the ammonia would react with itself and start turning back into those. So at the beginning, there was a very little bit of ammonia because it had just started being made, so they weren't really colliding with each other. And so the rate of reaction was slow. And then we got more and more of these as these reacted, and the rate of reaction started to increase. But then they started to disappear because they turned into that. And so the rate of reaction slowed down. The rate of reaction over here, as these start turning back into this, we get more of these on this side, and their reaction starts to speed up. So this graph starts to go up. So, I mean, I can go on forever, but the idea of this is that in any reversible reaction, we reach a point called equilibrium where the speed of both reactions, as in by both reactions, I mean the forward and the backward reaction, ends up being the same. So the speed at which this is turning into this is the same as the speed at which that is turning into that. And when that happens, it kind of cancels itself out, which means that whatever you've got, so if I've got this much ammonia and this much of nitrogen and hydrogen, okay, their amounts stop changing because as this is turning into this is turning into that at the same rate, which means that, like I say, that the rates kind of cancel each other out. Nothing extra is being made. We stop making any more. And we call that equilibrium. Equilibrium is reached when the rate of the forward reaction equals the rate of the backward reaction. You need to say that, okay? Forwards left to right, backwards right to left, like English. However, and this is where the actual question comes in, somebody determined that when you reach this equilibrium situation, there are things you can do that will temporarily speed up one of the reactions. So it means that it'll speed up the reaction this way, which means you'll get more of this stuff for a while before it again balances itself. Similarly, there are ways if I want to increase this side, I can do that temporarily to get more of one of the products that I want. So if I was doing this reaction, I'm actually doing it to make ammonia. We use ammonia for like fertilizers and cleaning products. Now, the question was about something called Le Chatelier's principle. That is a principle that if you change the conditions of this reaction, you can change the amount of one of the products or both of the products. And the two conditions you need to be able to explain are temperature and pressure. And for each one, there's a different explanation. Now, in any reversible reaction, one of the directions is exothermic and one of the directions is endothermic. See, all of this comes together. So in this particular, and you will be told in the question, usually explicitly, which way is which. Now, for this one, I'll tell you now that this way is endothermic and this way is exothermic. So when we turn hydrogen and nitrogen into ammonia, we release energy. When ammonia turns back into that, it takes in energy. Essentially, it can work both ways. Now, in terms of all you need to know is that if you increase the temperature of a reversible reaction at equilibrium, you need to just know which way you go. Do you get more of this side or do you get more of this side? That's all you need to be able to understand. So if you increase the temperature of this reaction, what you need to do is go in the direction, whichever way the endothermic direction is. And I've told you, they will tell you in the question usually which way that is. So If that's the endothermic direction and I increase the temperature, I will produce more hydrogen and nitrogen. Okay, if I increase the temperature and less ammonia, therefore, if you get more of one side, you get less of the other. Essentially, it speeds up the backward reaction, which means you start getting more of this and less of this. And therefore, if I wanted if I wanted more ammonia, I would need to um, lower the temperature. So if I wanted more of this, I need to keep the temperature low. So I just remembered it as high temperature, endothermic direction. That's it. If you know that, you will be able to apply that to basically any situation. High temperature, endothermic. Okay. Is that the same as point of equilibrium? Yes. I'm going to say yes. Um, it is, yeah. The point of equilibrium is the same as reaching equilibrium, which is, again, the definition is the same. It is the point at which the rate of the forward reaction equals the rate of the backward reaction. So for temperature, what you have to remember is whichever way is the endothermic is where you go with a high temperature. So higher the temperature, the more of the endothermic side. And often we phrase it as the equilibrium moves to the left or in the left direction, which ticks off temperature. The only other thing you need to know is what happens when you change the pressure. Okay. If you increase the pressure, again, all you need to know is which side do you go on? Do you go on the left-hand side? Do you go on the right-hand side? Or how do you know which side we get more of? And the answer is you count. You count how many of the big numbers are on the left-hand side. There are 3 on that side and 1 there. That makes 4 altogether. How many are on this side? There's 2 on that side. When you increase the pressure, you get more of the side with fewer molecules, fewer, the smaller number. Um, that's what it is. Okay, so the smaller number on the pressure. So for temperature, the higher the temperature, the more of the endothermic side. The higher the pressure, the more of the side with the smaller number of molecules. So in this case, in this example, the 2 is lower than the 4. So if I increase the pressure, I produce more ammonia. How do you know where the point of equilibrium lies? I mean, I'm not sure what you mean by that question, but I'd have to clarify. But I think what you mean, the point of equilibrium at the beginning, it is in the middle, I suppose. It's in the middle, and then it can move left or right depending on what conditions you change. And as I just explained, if you increase the temperature, it moves whichever side the endothermic direction is. So if it's on the left, it goes to the left. If endothermic is on the right, it moves to the right. If you increase the pressure, you can move it left or right as well, depending on where the smaller number is. So to start with, every reversible reaction reaches equilibrium. Think of it as just being in the middle, right? Because it means that it's neither, both sides are the same rate. And then you can move that left or right by changing temperature or pressure. Okay, that hopefully clears up a little bit of Letelier's principle, but I can go through it with you tomorrow if you want more questions on it. And then chemistry paper 1 topics like hydrogen fuel cells. Let me just do hydrogen fuel cells briefly, because it is a bit of a tricky one. I think I might have a textbook open, so I'm just going to go straight to the textbook for this. In fact, do I have some notes on it? I might even. Um, Phenomenal. Right, I got some. I'll just look at, in fact, what we'll do is, okay, we will just go through this. I'll just go through these notes and hopefully it'll be reasonably helpful for you. And then we'll recap just do a chemistry paper 1 at random, just very, very quickly. But what we'll do is we'll do this after a very short break. So I'll just take 5 minutes there to lock up properly. So I'll be back in 5 minutes. Right. Okay. I'm going to just go through these notes on this to give you an idea of this, and then I might, depending on time, I'll go through a paper as well. So, um, hydrogen fuel cells. Okay. Um, Firstly, a cell, as it says here, is just a system that contains chemicals which react and produce electricity. What you got here? And what you have in a cell is two different electrodes, so different materials here, so copper and zinc in this particular picture anyway, that are in contact with some solution, which is an electrolyte, which conducts electricity. Um, and that's all a cell actually is, but then you have to understand how this creates electricity. So there is a chemical reaction between the electrode, so copper in this case, and the electrolyte, which creates a potential difference, I suppose that's the proper word of it, between the electrodes. And we get electricity as a result. Now, what you need to realize is that, before I read the rest of this, is that the difference in reactivity between these two metals results in a bigger voltage being produced. So if zinc is very reactive, way more reactive than copper, then you'd get a bigger voltage. So the difference in reactivity creates the bigger voltage. Um, as it says here, the bigger the difference in the reactivity, the bigger the voltage of the cell. If it's the same metal, then you would get zero voltage because their reactivity is exactly the same, obviously, with the same metal. And what we can do with these questions is sort of the way the questions work on this is that they give you some results of different metals that they use, and you have to figure out which is the most reactive and which is the least reactive based on what you've got there. So we've got a cell here with copper and some other metal, some other metal. Um, and what they're going to keep doing is they're going to keep changing this metal. And in every case, it tells you that copper is the least reactive. Okay, so it's the less reactive of the two every time. We're just going to change the metal on the right here to make it, well, different, and it'll become more and more reactive. And then they give you a result in this table. So obviously, every time we used copper on the left one, and then we tried it with zinc, tin, iron, and chromium. And as I said earlier, if something is more reactive than the left-hand metal, you would get a bigger voltage. So because this is the biggest number, it's telling me that zinc is the most reactive of these four because we know copper is the least reactive, and because zinc with copper produced the biggest voltage, it means that zinc's the furthest away in terms of reactivity from copper. So in this question, you have to create um, an order of least reactive to most reactive. Well, copper's definitely the least reactive, so it goes last. Now, because zinc had the biggest voltage with it, it means that it's the most reactive. So that's at this end. And then it just goes in order of the numbers. So the next biggest voltage was from iron. So iron is more reactive than copper, but not as much as zinc because zinc produced a bigger voltage. So copper goes next. Oh, no, sorry, I mean iron goes next. And then the next one down will be chromium, and that's third one. And then the next one is tin, because that's the next one. So it's just basically putting it in order of these numbers. It gets a little bit more complicated with negative numbers in a second. Um, so as it says here, voltages may also be negative depending on which side of the cell the most reactive metal is on. So in this case, because we left copper on the left-hand side every time, we always got a positive number. But if you had swapped these over a little bit, you could have got positive and negatives, which doesn't change too much. But let me just show you an example of an answer. So a student set up a simple cell similar to the one in example one. They kept iron as the left-hand one, but iron isn't necessarily the least reactive one anymore. And these were the results they got when they did zinc, tin, lead, and aluminium. So they got 0.32 with zinc, and then they got some negative numbers, and they got a big one with aluminium. Now, here, the metal that leads to the most positive voltage, that would be aluminium, is the most reactive. The metal that gives the most negative will be the least reactive. So aluminium is the most reactive in this case, because it got the biggest positive value. Now, the biggest negative value was lead, so that goes at the other end. And then the others kind of go in between. So The next lowest was tin, which is minus 0.3, so tin goes there. And then the next biggest positive was the zinc, which is 0.32. So that goes next to the aluminium. Now, iron goes in the middle. So iron is kind of the bit that um, where the change happens, the positive to negative. So iron ends up being in the middle here because it gave negative values with tin and lead, which meant that iron is more reactive than tin and lead. And it gave positive values with aluminium and zinc, which means it's less reactive than aluminium and zinc. So that's how you determine the position of the left-hand electrode, is that if it gives negative values with anything, it means that it is more reactive than those things. If it gave positive values, then it is less reactive than those things. And putting all of that together allows you to position these in the way that it does in this table. Um, and then that's kind of it, isn't there much? But that's really the main stuff in this topic. Um, then there's a battery, then there's rechargeable batteries. Um, and then I'll just talk about fuel cells next before we just do a paper. Um, I'll just skim through one triple science paper, whatever the most recent one was. A fuel cell is an electrical cell that's supplied with a fuel and oxygen and efficiently transfers the energy released by the reaction between them as electricity. The fuel enters at one side where it becomes oxidized. So remember, oxidation is the loss of electrons, if you remember, that's what oxidation is. Oil rig, and it sets up a voltage within the cell. Um, this voltage powers the device that the fuel cell is connected to, such as a car. So the oxygen enters the cell at the other side. So on one side, we supply the fuel, and on the other side, we supply oxygen, where it reacts to form water. So the only example really you need to know is something called the hydrogen oxygen fuel cell, where hydrogen is used as a fuel and oxygen obviously comes in the other end and it releases energy. Um, and there's a bit of detail here, but you have access to these slides if you want to read through it. The electrolyte is often a solution of potassium hydroxide. Don't need to know that. So hydrogen goes into one side, oxygen goes into the other side. Um, as I said, at the negative electrode where the hydrogen is, that's the fuel. Remember, the fuel loses electrons. So hydrogen loses electrons. When hydrogen loses electrons, it becomes a H plus ion. That's what oxidation is, the loss of electrons. And the H plus ions in the electrolyte move to the positive electrode. At the positive electrode, I think that should say negative. Uh, Yeah, I'll double check. I'm pretty sure that should say negative. Anyway, the positive electrode, oxygen gains electrons and reacts with the H plus ions to form water. This is reduction. Again, reduction is gain, oxidation is loss. Try and remember oil rig. And then because we've got ions now, we basically get electric current flowing. So this is an example of a slightly complicated hydrogen oxygen fuel cell. There's a picture here illustrating what is happening. Crucially, just remember, something is being reduced, something is being oxidized, and the fuel is always the one that's being oxidized. It is losing electrons. So in the case of hydrogen, it becomes H plus ions. And then the oxygen is gaining electrons and it becomes negatively charged, O2 minus ions. And so we end up with a hydrogen fuel cell, in which case things flow around and we get a charge. But really, the key is, with most questions, it's about understanding that this oil rig is happening. There are some half equations here, which are basically the same as, well, I think that one you have to learn when you actually get to it. But yeah, that's essentially it. Right. And then there's a few details about um, problems with this stuff um, that you might get asked. Like hydrogen is great to use as a fuel, um, but it takes up loads more space than a battery. It is also explosive. Um, and often the hydrogen comes from hydrocarbons, which means that um, it has its own negative impact, which you, I'm sure, are aware of. Right. Lastly, I will just open up one chemistry paper. By the way, for those of you, if any of you are still here doing combined science, this particular topic isn't on it, but I am going to open up a triple science paper now. Um, paper one, I'll just stick to. one. And all I'll do is I'll just go through it directly on here rather than write anything. Um, I might need to actually. We'll see. Okay. Right. Horrible first question. This, if you remember, both in physics and in chemistry, you need to know about this plum pudding business. Um, this represents the plum pudding model of the atom. This is what we thought the atom looked like a while ago. Oh, there seems to be a question. Let's see. Um, anybody can stay here. Yes, you are more than welcome to stay or leave. There's no compulsion to stay here. But the describe the plum pudding model of the atom. So let's just go straight to the marks so we can talk through this together. Oh, if this was going to load. Um, so firstly, what I would say before I even look at the mark scheme is that in the plum pudding model, um, there is a sphere of positive charge that's spread out, and there are electrons stuck inside it, or something like that. Let's just see what it says here. A ball of positive charge with electrons embedded. There you go. That's the proper word, but electrons stuck in it would be fine to explain that. Then they wanted the order of discovery of electrons, neutrons, and protons. Now, I'm fairly confident neutrons is last, which it is. Neutrons were the last one to discovered, and then goes electrons first, then protons. Again, if you didn't get that, that's not too big a deal. Very few atoms of the element tennessine have ever been identified. The atomic number is 117. Predict the number of outer shell electrons in an atom of tennessine. Give one reason for your answer. Use the periodic table. Now, I'm not going to open up the periodic table, but what would you have to do is find where this element is in the periodic table, and then see what group it is in. And then the group number will be the number of outer shell electrons. So apparently it is in group 7. Therefore, there are 7 outer shell electrons. That is what you would use to predict the number of outer shell electrons. Tennessine was first identified by a small group of scientists in 2010. Suggests one reason why it was not accepted as a new element by other scientists until 2015. Isn't it because very few atoms of it were identified? Oh yeah, that's right. Yeah, that's right. So remember, this applies to biology as well as chemistry, which is that whenever something new happens, like even a vaccine or anything like that, part of the process is that other scientists have to do something called a peer review. They have to check everything, um, and so that can take time. And that was the only answer to that question, incredibly. Um, Isotopes. Calculate the relative atomic mass of element R based on this calculation. So I'm just going to do this straight on the calculator to tell you how easy this is. You do 6, the mass number, times this percentage, but turn it into a percentage. So 0.0. If I know you don't need to do that, divide it by 100 at the end. Just do 6 times that, 7.6, plus the other number, 7, times the percentage, 92.4, and then divide your answer by 100, and you will get 6.924 to one decimal place is 6.9. That's all you need to do for a question like that for a very easy 3 marks. Right, this is the required practical again. So I'm doing the paper here, which hopefully this is the required practical about the polystyrene cup, which is all to do with temperature changes. So what do? Make sure you read these really carefully. Okay, you should do what I'm doing. A student investigated the change in temperature of a solution when different masses of ammonium nitrate were dissolved in water. Okay, I'm not seeing this paper, so I'm just telling you this. If you read this carefully, you should be able to identify from what you read what the independent and the dependent variable is. And it's often just in the first line that I just read. So when it tells you that they use different masses of ammonium nitrate, that means they're telling you that that's the thing they're changing each time. They're using one mass and a different mass and a different mass, which means that is the independent variable. And then the thing they're measuring is the dependent variable. So they're measuring the change in temperature, which becomes the dependent variable. So I don't know if that's going to be a question in a second, but what I'm telling you is that if you read these carefully, the answers are where they are. Another place where you'll find the independent variable when they give you these steps is in the last step, because the last step will always say something like, we're going to do this all again, but change this. And in this case, they've said the different masses of ammonium nitrate. So that would be the independent variable. And then whenever it says measure, that's where the dependent variable is, right? That is the question. I promise you, I didn't know that. Give the independent variable and dependent variable in the investigation. So, as it says in the mark scheme, the independent variable is the mass of ammonium nitrate. The dependent variable is the temperature, essentially. To be honest, we're more precise about it. Can you just say temperature? You can just say temperature because they're in brackets. So yes, the temperature. Okay, but I suppose we want to be precise of the lowest temperature reached by the solution. Here are the results. So when we did it with 4 grams, we got this lowest temperature, this lowest temperature. Is this because it's an endothermic reaction? I'm just trying to have a look. It must be because it's measuring the lowest temperature reached. Okay. Plot the data. I'm not going to do that. You can plot it yourself. Determine the initial temperature of the water. Extend your line of best fit. So what would happen here, just so you know, is you would plot a graph. So it goes 418, and as it goes up, that goes down. Oops. So you would have something like this kind of situation, okay? Now, and you draw a line of best fit. Now, to work out the initial temperature of the water, what you'd have to do is extend your line of best fit and see where it crosses the axis there. And according to the mark scheme, you end up with, I don't know, just to where it meets the y-axis. There you go. That's all you need to do. Okay. Right. And then they did this 3 more times, some reason, and they showed the results for 8 grams of ammonium nitrate. So for 8 grams, they did it 4 times in total. Here they are. And they calculated a mean. They recorded the mean lowest temperature for 8 grams of ammonium as 16.5 plus or minus 0.3. Why did they include plus or minus 0.3 after the mean lowest temperature? So let me see. Let me just check why that is. 16.8. It's to do with something called uncertainty. Um, so yeah. So that thing that you add um, is something called uncertainty. So when you do experiment many times and they're a little bit spread out, as they were here, then you work out something called uncertainty. Uncertainty should be the range divided by 2. I just want to make sure that is what it is. Yeah, so the range is the highest value, take away the lowest value. 16.8 take away 16.2 is 0.6, and you divide that by 2, and you get 0.3. That's where this comes from. They're basically saying that this is my average, but it could be plus or minus a little bit either side because of the fact that there's a range of answers here. So it gives you a bit more of a specific. What type of error is shown in by the result in table 3? I think it's just a random error, probably. Yeah, if in doubt, it's random. It's just if it's slightly different, they're random errors, basically. Right, this is a required practical. Okay, I'm going to do this really fast, this one. I like this practical. And you should too. Okay. Plan a method to make pure dry crystals of zinc chloride. Make sure you read this bit carefully. Because from zinc carbonate, okay, well, obviously they're telling you what you're starting with. You're starting with zinc carbonate and an acid. Now, the acid that you've got to use to get to zinc chloride is hydrochloric acid. You'll get a mark just for getting that right. Remember, there are only 3 acids. There's hydrochloric acid that gives you something chloride. There is nitric acid that gives you something nitrate. And then there is sulfuric acid that would give you something sulfate. So reading the question tells you which one you're going to use. The fact that it says chloride tells you you're using hydrochloric acid in this question. Okay, in terms of what happens, just so you know, you're supposed to know the ending of this, even though you don't really need to for this one. You're going to get zinc chloride, which is what you're trying to get to, plus water. And you're going to get some carbon dioxide given off because of the carbonate, which we can ignore because it's just going to be a gas that's given off. Right. When you do this experiment, it's really small. Um, okay, I'm going to do this somewhere else. Um, right. When you do this experiment, you're going to get your beaker. You're going to put um, some hydrochloric acid in it, and you're going to put your zinc carbonate in it. But you're going to put in an excess of zinc carbonate. You need to say that. The reason we need an excess of zinc carbonate is because we're trying to make sure that the hydrochloric acid fully reacts. You can make sure that one of the reactant finishes by making sure there's loads of the other reactant, because it means that that's the one that'll get left over. So that means that once you've done this, you will have inside your solution some zinc chloride and some water. The CO2 will be given off, you can ignore it. But you will also have this excess zinc carbonate, which didn't react, or the unreacted zinc carbonate. What you need to do first is get rid of that. Now, that's going to be a solid inside this solution. How do you get rid of a solid from a solution? You filter it out with some filter paper. So you put all of that stuff in there. Your excess zinc carbonate will stick to the sides here, leaving you with only zinc chloride and water. So remember, what you're trying to get to is the zinc chloride by itself. Last thing you're going to do is get rid of the water by heating this to evaporate the water. And then when you leave the rest of it to cool down, you will end up with zinc chloride crystals, or a pure, I think this is a pure dry, yeah, pure dry crystals. That's how you do the full practical involving that. Right, let's get through the rest of this. Name two other substances that can be each be reacted with a dilute acid to make zinc chloride. The answer is zinc on its own. That'll give you zinc chloride, and zinc oxide. That could also be used, and actually zinc hydroxide. There should be all three of those in the mark scheme, I think. There you go. Zinc oxide and zinc hydroxide. All of them. This is oh my God. Right, this is what I did earlier, really. But in order to calculate the overall energy change of this reaction, what you would do is you'd add 436 to 346 and then take away two lots of 432 because you take away the right-hand side. So 436 plus 346 take away two lots of 432. That's going to be the answer. Why does this reaction release energy to surroundings? Again, as I told you, when you see these bond type questions, you have to explain why they're exothermic. You have to talk in terms of breaking and making bonds. So you'd have to say that the amount of energy taken in to break the existing bonds is less than the amount of energy released to form the new bonds. That's what you have to say. And I'm pretty sure the mark scheme will say something like that. The energy needed to break the bonds or energy released is greater than the energy needed. You see what I mean? It says it's about specifically the energy in terms of the bonds. You have to answer this in that way. Reaction profile. Finish this off. Lovely question. So it's exothermic, right? So it means that it needs to finish lower than where we started. So something like that would be fine. That's your overall energy change, and that's your activation energy. And that is the answer. HCl, outer electrons only. Okay, well, chlorine has got 7 outer shell electrons, which means it needs to gain one more. Hydrogen has got 1 outer shell electron, which means it needs to gain one more. H with its 1, and then that's how HCl. Methane is a gas at room temperature. Polythene is a solid at room temperature. Explain why. Okay, well, you need to explain that this is a simple covalent molecule, and simple covalent molecules have weak intermolecular forces. You have to say these words, weak intermolecular forces, which take very little energy to break, which means that they tend to have very low melting and boiling points. Okay, so these kind of things that are just drawn like this, even the same one that we just, the HCl that I just drew, because they're small and simple, that's the whole diagram. They have low melting and boiling points, and you want to say because of the weak intermolecular forces, which need very little energy to break. That makes them more likely to be liquids and gases at room temperature. In this case, a gas at room temperature. This, though, because of this N, is a giant molecule. Giant molecules have got loads of bonds that takes loads of energy to overcome, which means they tend to be solid at room temperature. So the mark scheme for that last bit. Um, so that was all done. Right. Methane are small molecules, so weak intermolecular forces need very little energy to overcome, so they have low melting and boiling points. And that pretty much that. And that actually is all the marks. You could have just said what I just said. Or you could have said the opposite, which has got it's much larger, it's got stronger intermolecular forces, they need more energy to break, so they have high melting and boiling points. So you don't have to say all of that. Half of it is fine. It'll get you all the marks. Acid and alkalis. What is meant by a weak acid? A weak acid is one that partly ionizes in water, whereas a strong acid fully ionizes in water. That should be what it said. There you go. Partially ionized, whereas in the other one is fully ionized. Um, oh God, the concentration. What combination of change increases the concentration of an acid? God. Um, it won't be halving the amount of acid dissolved. Okay, so if you double the amount of acid and halve the volume of the solution, you would get a stronger acid. Think of those orange squash drinks. How could you increase the strength or the concentration of it? You could reduce the amount of water you put in, and you could increase the amount of the orange stuff you put in. That's basically what we're talking about here, where the acid is the orange stuff. Um, so hopefully that's the answer. Mass of the acid is doubled, the volume is halved. There you go. That makes the whole thing stronger. Um, this is a titration with an indicator. God, you have to know the indicator. So there's like methyl orange. There's that one with a long name with P, and there's litmus as well. So you can say litmus and use blue to red. That might be the easiest one. But you need to remember any of these, which are the color changes for those indicators, not universal indicator. It says give 1 mark for universal indicator, but that isn't what you want to do. Um, the formula that makes something alkaline, well, acids are H plus ions, the other ones are OH minus ions. I'm not going to do the titration question. I'm fairly certain if you look through our social media, TikTok specifically, I've almost 100% done this exact question at some point on it recently, because I just did all the calculation ones when I was bored one day. Right, I might not do too much more. Let me see what else there is here. Okay, that's just evaluating. Very common question. It was in the test probably that the ones in year 10 did, I think. How metals conduct electricity? You must say the same points, which are delocalized electrons carrying the charge through the structure. That's usually the three specific things, I think. We'll check. So delocalized electrons, which can carry the charge and then through the structure for the third mark. I'm hoping that is the correct answer. Um, delocalized electron, carry the charge, moving through the structure. There you go, 3 marks every time. Um, why alloys do not conduct electricity as well as pure metals? The thing about alloys is that you distort the layers. That's the thing that you always have to say about an alloy. That's what makes them stronger usually. But I guess that means that the electrons don't flow through as easily. Distort the layers, the movement of electrons is restricted. Okay, so you have to apply your knowledge a little bit there. Most alloy questions ask you why alloys are harder than pure metals, and you say it's because the layers are distorted because you mix in different sized atoms, which means the layers can't slide over each other. But this is not about the layers sliding over each other, it's about the electrons traveling through. And so you have to apply your knowledge to that situation. I'm not going to do this for about electrolysis, but I mean, it's a 3 that goes there. If in doubt, it's the same number that's here, 3. Um, okay, is there anything else? That's just knowing electrolysis really well. Why does argon not form compounds? You need to explain that it's got a full outer shell of electrons, which means that it does not react because it doesn't need to get a full outer shell because it's already got a full outer shell. Um, fine. Barium reacts with acid, probably gives off a gas, fizzes, I don't know, that sort of stuff. It's usually the same sort of answers. Fizzes, forms a solution, gets hot. Yeah, fine. You can't, by the way, just to be clear, a mistake I just made, which I always do. Fizzing and giving off a gas are not two separate points when you answer these kind of questions. They are the same thing. So just remember that. A balanced equation. Yeah, right. Reduced. Well, answer in terms of oxygen. The Fe2O3 has been reduced here because reduction in terms of oxygen is the removal of oxygen. So we had iron oxide here that has become iron. So what's been reduced is the iron oxide. We've removed the oxygen from it. That's calculation. Can't have time for that. And again, this particular question, if you look on the social media, I definitely most what I've tried to do on the social media stuff is I've tried to do all the calculation stuff because it's just more, I don't know, entertaining. So most questions involving any calculations at some point I have done, and there is a video that exists for it, including this one because I watched it today. This exact question. And then this is about nanoparticles. Okay, I think this is reading the question really. Yeah, fine. Need to know about nanoparticle. I've done this question before as well, I promise. And that is the only one. Just on nanoparticles, let me just quickly finish off with this because it is very specific to the triple stuff. The main things to know about nano, it's a very small thing here. Firstly, they're obviously very small, right? Nano, right? But the stuff that it says here is pretty much all you need. Well, I say all, it's quite a lot, but this is what you need to know about nanoparticles. It's that they have a high surface area to volume ratio, which means you can use a small amount of them and to get as a catalyst. They can be absorbed more easily by the body. They can conduct electricity, um, and they have antibacterial properties, and they can cover the skin better. And usually, one of those things can be used to answer any question on them. So, self-cleaning windows are coated with a layer of nanoparticle of titanium dioxide. It helps sunlight break down dirt particles. It attracts water, so dirt is washed away by the rain. Nanoparticles are used instead. Let's have a look at the answer to finish. So, as I said, most questions involving nanoparticles, I say most of them, one of the answers is that they have a high surface area to volume ratio. Um, and that's usually a really easy mark. And then you have to apply this to the situation, which means that you need less of it to get the same effect. So the whole process is cheaper, basically, because you don't need to use as much of it on the window, essentially, because it's got a high surface area to volume ratio. Right. Hopefully that is useful. I am going to stop there and meet again next week. If you have any other specific questions, then feel free to send them and we'll get back